Alright, so here they're saying which of the following pair will not produce dihydrogen gas. Okay, so we have to go through each of them and we have to check in which reaction you do not get dihydrogen gas as a product. Alright, so first you have copper plus dilute HCl, and in fact this is the reaction where you don't get dihydrogen gas, because here basically you need to look at the tendency of formation of, one second. So here you need to look at the tendency of formation of copper to copper plus, right? So that tendency is very low, okay? When you already have HCl, when you already have hydrogen in +1 oxidation state, this reaction is not going to be favored. Why? Because it's easier for hydrogen, right? It's easier for hydrogen to exist in +1 than to take copper to +1. Okay, very simple things. What am I talking about? I am simply talking about electrode potential. I am talking about the reactivity series, where we know that hydrogen is more reactive, so it is more likely than that hydrogen will be in the +1 oxidation state instead of copper being in the +1 or in the +2 oxidation state, right? Oversimplified electrochemical series, but yes, that is what happens. So what is happening here? Here you will not, the reaction will not be proceeding. Okay, so here what happens is there is going to be no reaction. Then you have Fe plus H2SO4. So here what you get is, I'll write it here, you get FeSO4 plus H2. So H2 is released here. Okay, so yes, definitely dihydrogen is released. So yes, this can produce dihydrogen gas. Then you have magnesium plus steam. So when you allow magnesium to react with steam, what happens is you get MgO, magnesium oxide, and then again your dihydrogen is released. Okay, and this is a reaction that will happen only with steam, not with hot water, or not with normal water. Cool, great. So yes, this also happens. Then you have sodium plus alcohol. So here what you get is an ion called sodium alkoxide ion, and then you get dihydrogen. So if you take your alcohol as ethanol, okay, so then you get sodium ethoxide ion. Okay, so you get Na plus your alcohol minus the hydrogen, right? So let me write down the specific reaction in case of ethanol. Okay, this is not too easy to understand right now, but just remember this as a reaction. You will understand this going forward in your alcohols, ethers and phenols chapter. So here what you have is sodium plus alcohol, I'm taking as ethanol. Okay, C2H5OH. So what you're doing here is, this extra hydrogen that you have, you're removing that. I should not be saying extra. We're removing the hydrogen from there, as a result of which what you get here is your negatively charged ion. So you have C2H5O minus. This is the anion, and the cation is going to come from sodium. So here you will have Na plus. Okay, so this is your sodium alkoxide ion plus H2 is released. This hydrogen that you took out from here is released as dihydrogen gas. This is one of the tests for alcohol rather. Don't worry, it will all come to haunt you later in your 12th standard. For now, what do we need to know? Yes, this reaction is possible, and yes, dihydrogen is released from this reaction. So where is dihydrogen not released? In option A. So in option A, what do you have? Dihydrogen is not released, so it will not produce dihydrogen gas. So option A is going to be the right answer to this question. Alright, so here in this question, they're asking us, in which of the following reactions does hydrogen act as an oxidizing agent? Okay, so let's see. So we have 4 options. We have 4 different reactions. We actually need to see what are the products of this reaction and where we see hydrogen bringing about an oxidizing change, right? So where will hydrogen act as an oxidizing agent? Wherever you see that before the reaction, your reagent had a lower oxidation state, and after the reaction, your reagent has a higher oxidation state, right? Wherever your other reagent, right, hydrogen itself should be undergoing reduction, and your other reagent that you have, that should be undergoing oxidation. That is how you can say that hydrogen has been the oxidizing agent if it is bringing about a change of oxidation in the other reactant or reagent. Okay, all right, let's see. So you have H2 plus F2 here. As a result of this reaction, what you get is HF. So initially, when we started off with fluorine, right, on the reactant side, you had fluorine in the oxidation state of 0, and on the product side, you have fluorine in the oxidation state of -1. Correct? So here, what is the change? The change is fluorine is getting reduced, right? So fluorine is getting reduced, which means here hydrogen has behaved as a reducing agent. Okay. Then you have option B, H2 plus SiCl4. This gives you silicon plus HCl, right? Since I'm only concerned by silicon, I'm not going to be talking about anything else. So here what you have is silicon before the reaction was in the oxidation state of +4. After the reaction, you have 0. Okay, so what do we get here? We get here, so silicon is going from +4 to 0, which is reduction. So here also hydrogen has behaved as a reducing agent. Okay, then we have option C, sodium plus H2. Okay, this will give you sodium hydride. Okay, so here you have sodium in the oxidation state of 0 before the reaction. After the reaction, it is in the state of +1. So what can we see? We can see that sodium underwent oxidation and this change is brought about by hydrogen. So here it is acting as an oxidizing agent. Alright, lastly, what do we have? We have copper oxide plus hydrogen giving us copper. Okay. So here what happens, initially you had copper in +2 oxidation state. After the reaction you have copper in 0 oxidation state. What is the change that we see? The change that we see is nothing but reduction. So here also hydrogen is acting as a reducing agent. So overall there's just one place where hydrogen acts as an oxidizing agent, which is here in option C. So option C, Na plus H2, is going to be the reaction where you can see that hydrogen acts as an oxidizing agent, which means option C is going to be the right answer to this question. Alright, so here they're asking us the number of neutrons in deuterium is going to be what? Is it going to be 1, 0, 2 or 3? Okay, so basically, first of all, let's talk about hydrogen. So hydrogen, basically, if I were to denote it in this form, right, where M is my element, A is my mass number and Z is my atomic number. If I want to denote hydrogen like this, then it is going to be H11. What does it mean? It means that in hydrogen, your atomic number is 1 and your mass number is also 1, which means your nucleus, right? The nucleus has just one proton. That is all that is in the nucleus. Okay. Now, an isotope of hydrogen is deuterium. Okay. And what happens in the case of deuterium? You have hydrogen 2 and 1. Okay, sometimes this is also represented as, I will use a different color here. Okay, yeah, so this is also represented as D21, okay, or D2. Okay, all of that is deuterium. So here what you can see that the mass number has become 2. So since the identity of the element is the number of protons, you have just one proton. So what else can you have in the nucleus, right? What other nucleon can you have? You can have either proton or neutron. So deuterium has one neutron. I know that I have, made it very, very simple. Maybe I've oversimplified it, but it's okay. Right now we're investing our time in getting to know hydrogen and all of its brothers and sisters. Okay, so yes, here you have deuterium, in which case you have one proton plus one neutron in the nucleus. The question is asking you for the number of neutrons, which is 1. So which means 1, as suggested in option A, is going to be the right answer to this question. So here they're saying when dilute H2SO4 is electrolyzed using platinum electrodes, the gas evolved at the cathode is going to be what? Okay, options are O2, SO2, SO3 and H2. Okay, so here what you need to understand is that they are talking about the cathode and what happens at cathode. I hope you remember this, that at cathode we are talking about the reduction happening, right? So they are basically talking about what is happening in the reduction half of the reaction. So let's see. Okay, so when you have dilute H2SO4, right, when you have the solution of dilute H2SO4 which you are putting up for electrolysis, what are the ions in the solution? So you have H plus, you have OH minus and H2SO4, right? This is coming from water, H plus and OH minus, and then you have H2SO4 which dissociates to give you H plus and SO4 2 minus. So we've already written H plus, so then you have SO4 2 minus. Okay, so you have these ions in the in your solution basically. Now when you talk about reduction, this H plus, Okay, this H plus is going to be the ion that undergoes reduction, and you basically get H plus gives you H2, right? Of course, if you want to be very technical about it, you can write H plus plus electron gives you H2, and here you get 2 and 2. This is what the half reaction is going to look like. Okay, so yes, now what happens at the anode? Now you have these two ions, right? You have your OH minus and you have your sulfate ion. Between these two ions, you need to figure out which one is going to get oxidized. So at anode, you will have oxidation, oxidation, and between your hydroxyl ion and your sulfate ion, you need to figure out which one of the two is easier to oxidize, right? Okay, so that's a different discussion. Here they have asked us where is the reduction happening. Of course, reduction is happening at cathode. We are asking you which gas is released at cathode, so which ion is actually getting reduced. You need to be talking about that. Okay, so H plus is getting reduced, as a result of which you get H2 dihydrogen gas that is released at the cathode, and that dihydrogen gas is here in option D, which means option D, H2, is going to be the right answer to this question. Okay, so here we have a fun question combining a lot of concepts. Basically, the fundamental idea here is concepts from gaseous state, okay, states of matter. So here, let's see, you have option A, the question is reading that a certain volume of H2 effuses from an apparatus in 1 minute. The same volume of ozonized oxygen, that is a mixture of O3 plus O2, took 246 seconds to effuse from the apparatus under identical conditions. Find the percentage of oxygen in the ozonized oxygen. Okay, so you have options. Okay, these are your percentages. So basically, what is the law or what is the formula that we're going to use here? That is nothing but Graham's law. Okay, and it's a very simple and straightforward approach that we are taking here. So basically, you know that Graham's law states that R1 by R2, or let's talk about it in terms of just rate initially. So rate is directly proportional to 1 by root m, or rate is inversely proportional to the molar mass. I'm going to use this form of Graham's law. You need to be very careful because, you know, like one thing you could do for saving your time in the examination is that you could, just learn the entire formula of Graham's law, okay? You could derive it, sure. You could also learn it, whatever is convenient for you. Okay, so rate is nothing but what? Volume effused per time, right? Volume effused divided by time taken for that effusion. Okay, now this they are saying is inversely proportional to root m. Volume is going to be same. Okay, they have said in the question that the same volume of hydrogen and another ozonized oxygen mixture. So substance 1 versus substance 2, same volume has effused in different amounts of time. So volume becomes constant, which means I can now say that time taken for that given effusion is going to be directly proportional to root m. And we're going to use this form. Okay, so you have T1 by T2 is equal to under root of M1 by M2, where what is M? M is nothing but molar mass. Okay, so you have hydrogen gas as the first mixture, and this took 60 seconds for effusion. And you have another mixture, I'll just call that mixture M, right? You have an oxygen plus ozone mixture which took 246 seconds, right? It took 246 seconds to effuse, same volume, but different composition, right? Different molar mass, which is why we see this discrepancy. They have said that all other conditions are identical. Very important. Okay, so now let's substitute these things into the formula and see what we are getting. So time 1 is 60 seconds divided by time 2 is 246 seconds is equal to under root of 60 seconds for dihydrogen. What is the molar mass of dihydrogen? 2 gram per mole. Okay, so since this is a ratio, as long as I keep my molar masses in the same units, we are good. So here I'll write 2 gram per mole divided by, let's say the mass of this mixture is M. Okay, cool. So far, so good. And what do you have? You have root M is equal to what? Let's see. So you have, let me just write it completely. So you have 60 divided by 246 into root 2 is equal to 1 by root m. So which means root m is equal to 246 into root 2 divided by 60. Correct? You can square it. So m is going to be equal to, or I am going to simplify this a little bit first. So please look very closely for the calculations. This will go once, this will go 41 times, right? So you have 41 into root 2 divided by 10 whole squared, which means the molar mass of the given mixture is going to become, 41 square. Now what is 41 square? I hope quickly calculate, pause the video and calculate it quickly. I'm going to write the answer here, okay? So 41 square is going to be 1681. And then what do you have? Into 2 divided by 100. This is the molar mass of the mixture. Or I can say that 100 m is equal to 1681 into 2. What is 1681 into 2? Let's quickly do it. So you have 2, 6, then you have 3 and 3. Okay, so you have 3362. Okay, keep this value. Keep this value. I'll call this value 1. Okay, now why did I keep this like this? Because they asked us for the percentage of oxygen in the ozonized mixture. So let's say you have O3 plus O2. So I'll say oxygen is X%, so which means ozone will be 100 minus X. Okay, what is the molar mass of each of these things? Molar mass of oxygen is 32 gram per mole. Molar mass of ozone is 48 gram per mole. Correct? Now, let's write down the equation. So, what you get here is 32x plus 100 minus x into 48 divided by 100 is equal to m, or this entire thing on the left hand side is equal to 100m. 100m, you know the value. So, this is going to be equal to 3362. Cool? Done. Now let's see, what do we have? We have 4800 minus 3362 is equal to 16x. Okay, so you'll get 1438. Yeah. So 16x is equal to 1438 and x is going to be equal to 1438 by 16. Calculate this. Okay, so here look at it. So you have 16 into 5 is 16 into 9. 16 into 9 is 144. Okay, so if I try to cancel this out, this is like barely falling short of 90. So I can say this is approximately 90. And with this approximation, you can get the answer, okay? Because take a look at your options. Very close to 90. I want a value that is very close to 90. You have only option A. That is 88.87, almost 89. Okay, that is the closest value to 90. Another value you have is 99.87. That is extreme. That is much greater than 90. So we're not going to be taking this. And C and D, can't even consider them. They're pretty far away. Right? So option A, 88.87% is going to be the right answer to this question.